Hello students, today we will start a new series of lectures of chemistry for class 12. Our discussions will be based on NCERT syllabus rationalized for the year 2023-24. In today's lecture, we will study about types of solutions and expressing concentration of solutions. All the points discussed in today's lecture are important. Please note down and make your notes accordingly. In normal life, we rarely come across pure substances. Most of these are mixtures containing two or more pure substances. Their utility or importance in life depends on their composition. For example, the properties of brass, that is, a mixture of copper and zinc, are quite different from those of German silver, that is, a mixture of copper, zinc, and nickel, or bronze mixture of copper and tin. 1 part per million of fluoride ions in water prevents tooth decay, while 1.5 parts per million causes the tooth to become mottled, and high concentration of fluoride ions can be poisonous. For example, sodium fluoride is used in rat poison. Intravenous injections are always dissolved in water containing salts at particular ionic concentration that match with blood plasma concentrations and so on. In Unit 1, we will consider mostly liquid solutions and their formation. This will be followed by studying properties of solutions like vapor pressure, colligative properties. We will begin with types of solutions and then various alternatives in which concentrations of a solute can be expressed in liquid solutions. I welcome you once again. Types of solutions. Solutions are homogeneous mixtures of two or more than two components. Homogeneous mixture means all components are uniformly distributed throughout the solution. Solvent is a component that is present in largest quantity. Solvent determines the physical state in which solution exists. Solute is the component that is present in smaller quantities. So, largest quantity is solvent, solute is smaller quantity in the solution. One or more components present in the solution other than solvent are called solutes. A binary solution is composed of two components. Solutions may be known as ternary and quaternary when it is made up of 3 or 4 components respectively. That means if 3 components are present, then it is called ternary, and if 4 components are there in a solution, then it is quaternary. Please see the table. The table shows types of solutions. So the type of solution can be gaseous solution, liquid solution, or solid solutions. In gaseous solutions, the solute is a gas, and solvent is also a gas. So mixture of, for example, mixture of oxygen and nitrogen gases form a gaseous solution. Similarly, they can be a liquid solute and a gas solvent, that is chloroform mixed with nitrogen. So chloroform is liquid and nitrogen is gas. The third type in the gaseous solution is solid, solute and gas solvent. For example, camphor in nitrogen. Liquid solutions. The second type of solution is liquid solutions. That is, gas is a solute and liquid is a solvent. For example, oxygen dissolved in water. In the next category of liquid solution is liquid solute and liquid solutions. And its example is ethanol dissolved in water. The third category in liquid solutions is solid solute and liquid solvent. Example, glucose dissolved in water. The third type of solution is solid solutions, where solute is a gas and solvent is solid. So please note, in solid solutions, the gas is a solute and solvent is solid. Example of such a case is solution of hydrogen in palladium. The next category in solid solutions is liquid solute and solid solvent. Example is amalgam of mercury with sodium. The last and final category in the solid solutions is both solute and solvent are solids. Example is copper dissolved in gold. Expressing concentration of solution. Composition of a solution can be described by expressing its concentration. The latter can be expressed either qualitatively or quantitatively. For example, qualitatively, we can say that the solution is dilute, that is, relatively very small quantity of solute, or it is concentrated. So, the qualitatively, the concentration of solution can be dilute or it is concentrated. That is, concentrated means relatively very large quantity of solute. But in real life, these kinds of descriptions can add to lot of confusion, and thus the need for quantitative description of solid. There are several ways by which we can describe the concentration of solution quantitatively. First first way is mass percentage. That is, the mass percentage of a solution is defined as mass component in the solution divided by total mass of the solution into 100. Let it be equation 1. So I will repeat, mass percentage weight by weight is defined as mass percentage of a component equals mass of the component in the solutions divided by total mass of the solution into 100. For example, if a solution is described by 10% glucose in water by mass, it means 10 grams of glucose is dissolved in 90 grams of water, resulting in 100 gram solution. Concentration described by mass percentage is commonly used in industrial chemical applications. For example, commercial bleaching solution contains 3.62 mass percentage of sodium hypochlorite in water. The next one is volume percentage, volume V by V. V represents volume. So volume percentage of a component is volume of the component divided by total volume of the solution into 100. Let it be equation 2. Example of V by V is 10% ethanol solution in water means that 10 ml of ethanol is dissolved in water such that the total volume of the solution is 100 ml. Solutions containing liquids are commonly expressed in V by V in this unit, that is volume percentage. For example, a 35% V by V solution of ethylene glycol, I repeat, ethylene glycol, an antifreeze is used in cars for cooling the engine. At this concentration, the antifreeze lowers the freezing point of water to 255.4 Kelvin, that is minus 17.6 degree centigrade. The third category is mass by mass. The third category is mass by volume percentage. I repeat, the third category is mass by volume percentage, that is W by V. Another unit which is commonly used in medicine and pharmacy is mass by volume percentage. It is the mass of solute dissolved in 100 ml solution. The next category is parts per million. When a solute is present in trace quantities, it is convenient to express concentration in parts per million, that is, it is written in short form as ppm and is defined as parts per million. Parts per million is equal to number of parts of the component divided by total number of parts of all components of the solution into 10 to the power of 6. See, multiplier in parts per million is into 10 to the power of 6. Let it be equation 3. As in the case of percentage, concentration in parts per million can be expressed as mass to mass, volume to volume, and mass to volume. So, ppm can be either mass to mass or volume to volume or mass to volume. A liter of seawater weighs 1030 grams, contains about 6 into 10 to the power of minus 3 grams of dissolved oxygen. We'll continue with the topic expressing concentration of solutions. Concentrations in parts per million can also be expressed as mass to mass, volume to volume, or mass to volume. For example, a liter of seawater which weighs about 1030 grams contains about 6 into 10 to the power of minus 3 grams of dissolved oxygen. Such a small concentration is also expressed as 5.8 grams per 10 to the power of 6 grams, that is 5.8 ppm or parts per million of seawater. The concentration of pollutants in water or atmosphere is often expressed in terms of milligrams per milliliter or parts per million. So let us summarize the various ways of expressing concentration of solutions, which is shown in the table on your screen. The first one is mass percentage. Its symbol is percent W by W, capital W, small w by capital W, and its formula or definition is expressed as mass of the component in solution divided by total mass of the solution into 100. So numerator and denominator both are mass. As we know, mass is not affected by changes in temperature. Hence, the effect of temperature in mass percentage is nil or 0. So, there is no effect of temperature on mass percentage. The next one is mass per volume percentage. It is written, its symbol is percent W by V. So its formula or definition is mass per solute, mass of solute divided by total volume of the solution. Please note, numerator is mass and denominator is volume into 100. So since volume factor is there, it is affected by the changes in temperature. Next one is volume percentage. Volume percentage is percent V by V, capital V. So its symbol is V by V. So its formula is volume of solute divided by total volume of solution in ml into 100. So both the components in the numerator factors, numerator and denominator have volume. Hence, it is affected by temperature. The next one is strength. So it is grams per liter or grams per decimeter cube. Decimeter cube. Please note. So component it is grams per liter means numerator is mass. Mass of solute in grams divided by volume of solutions in liters per decimeter or decimeter cube. So because volume is there, it is affected by the changes in temperature. The next one is parts per million. That is written, its symbol is ppm, parts per million, and its formula or definition is number of parts of solute divided by total number of parts of all components of the solution. Please note here, there is it is only a number in numerator and number in denominator. So ppm. So it is not affected by changes in temperature. Mole fraction. It is represented by symbol X and it is defined as X is equal to Na divided by Na plus NP. We will study about in detail about mole fraction, molarity and molality in the next slides, next 3-4 slides. But you please remember, mole fraction is represented by the symbol X. X is equal to Na divided by Na plus Nb, small n and small nb. It is not affected by changes in temperature. Molarity. Molarity, the term molarity is represented by symbol capital M. It is defined as moles of solute divided by volume of solution in liters per decimeter cube. Because solution volume is there in denominator, it is affected by the temperature. The last and final one in this series is molality. Molality is represented by the letter small m. So its definition or formula is moles of solute divided by mass of solvent in kg. So numerator is number moles of solute divided by mass of solvent in kg. So it is not affected by changes in temperature. Now we will define mole fraction. There is another mole fraction. Mole fractional is the commonly used symbol for mole fraction is x, and subscript of x denotes the component. It is defined as mole fraction of a component is equal to number of moles of component divided by total number of moles of all components of the solution. Let it be equation 4. This definition we have described in the previous slide also. Example, in a binary mixture, if the number of moles of A and B are Na and Nb, small na is the number of moles of component A, and small Nb, N subscript B is the mole fraction of A, will be Xa is equal to Na divided by Na plus Nb. So in this mixture there are two components, component A and component B, and its number is number of moles in A is Na and number of moles in B is Nb. So let it be equation 5. For a solution containing I number of components, we have x1 is equal to n1 divided by n1 plus n2 plus etc. Up to n subscript I. It can be also be written as ni over sigma ni. Let it be equation 6. It can be shown that in a given solution, sum of all mole fractions is unity, that is 1. That is x1. If a solution contains different components x1, x2, etc. up to xi, then the sum of x1 plus x2 plus etc. up to xi equals 1. Let it be equation 7. Thus, mole fraction unit is very useful in relating some physical properties of the solution, say vapor pressure with concentration of solution, and quite useful in describing the calculations involving gas mixtures. Example 1. Calculate the mole fraction of ethylene glycol C2H6O2 in solution containing 20% of C2H6O2 by mass. Assume that we have 100 grams of solution. This solution will contain 20 grams of ethylene glycol and 80 grams of water. Because it is given that the solution has 20% of C2H6O2 by mass. So molar mass of C2H6O2 will be C2, that is C2 is 2 into 12 because atomic weight of carbon is 12, plus H6 will be 1 into 6 and O2 is 2. Simplifying, it becomes 62 grams per mole. So moles of C2H6O2 will be equal to 20 divided by 62 grams per mole, or it is equal to 0.322. Moles of water will be 80 grams divided by 18 grams per mole. 18 grams is the atomic weight of water. So that is equal to 4.444. 4.444 mole. So therefore, the mole fraction X glycol will be moles of C2H6O2 divided by moles of C2H6O2 plus moles of hydrogen, moles of H2O. Therefore, that becomes 0.3222 mole divided by 0.322 mole plus 4.444 mole. That equal to 0.068. Similarly, we can calculate for mole fraction of water, that is X subscript water is equal to 4.444 moles, which is the moles of water, divided by 0.322, that is moles of C2H6O2 plus 4.444 mole, that is equal to 0.932. Mole fraction of water can also be calculated as 1 minus 0.068, that is mole fraction of glycol. Next we will take up molarity. Molarity M is defined as the number of moles of solute dissolved in 1 liter or 1 cubic decimeter of solution. Hence, it is represented by the letter capital M. So, molarity M is defined as number of moles of solute dissolved in 1 liter or 1 cubic decimeter of the solution. So, writing it in mathematical form, molarity is equal to moles of solute divided by volume of solution in 1 liter. That is, let it be equation 8. For example, 0.25 mole per liter or 0.25 m. So, we can write molarity as 0.25 mole per liter or 0.25 capital M. Solution of NaOH means that 0.25 mole of sodium hydroxide NaOH has been dissolved in 1 liter or 1 cubic decimeter. Let us take an example. Let it be example 2. Calculate the molarity containing 5 grams of sodium NaOH in 450 ml. Please note here denominator is in molarity, denominator is volume. Solution. So mole of NaOH equals moles of solute divided by volume of solution in liter. So that can be written as 5 grams divided by 40 grams per mole, that is equal to 0.125 mole. So volume of solution in liters is 450 milliliter. It is given volume of the solution 450 milliliter, that can be written as 450 ml divided by 1000 ml per liter, milliliter per liter. So molarity is equals 0.125 mole into 1000 milliliter per liter divided by 450. So that is equal to 0.278 mole per liter, mole per liter, or 0.278 moles per liter. It can also be written as 0.278 mole per decimeter cube, because liter is decimeter cube here. The next one is molality. Please remember the spelling molality. Molality is, the symbol of molality is small m. So molality m is defined as the number of moles of solute per kilogram of the solvent, and it is expressed as molality small m is equal to moles of solute, number of moles of solute divided by mass of solvent in kg. Let it be equation 9. Let us take an example. For example, 1 mole per kg, that is 1.00 small m, means it is 1 mole molality per kg, 1 mole per kg. This m represents mole per kg. Solution of KCl means that 1 mole, that is 74.5 grams of KCl is dissolved in 1 kg of water. Each method of expressing concentration of the solution has its own merits and demerits. Mass percentage, parts per million, mole fraction and molality are independent of temperature, whereas molarity is a function of temperature, as we have seen it in the table shown in the earlier slide. This is because volume depends on temperature and mass does not. So let us take one example. Calculate the molality of 2.5 grams of ethanoic acid CH3COOH in 75 grams of benzene. So let us solve it. Molar mass of C2H2O2 equals 2 into 12 into 2 plus 1 into 4 plus 16 into 2. Therefore, molar mass of C2H4O2 is 60 grams per mole. Therefore, moles of C2H4O2 equals 2.5 grams. It is given 2.5 grams divided by 60 grams per mole. That is equal to 0.0417 mole. Mass of benzene in kg is 75 grams. It is given 75 grams per 1000 grams per kg. So that is equal to 75 into 10 to the power of minus 3 kg. Therefore, molality of C2H4O2 equals moles of C2H4O2 divided by kg of benzene. Substituting the values, we get molality of C2H4O2 equals 0.0417 mole into 1000 grams per kg, or 75 grams. That is equal to 0.556 mole per kg. That is the answer. Next, we will answer some of the multiple choice questions of section 1.1 and 1.2. Question number 1. Homogeneous mixture of two or more than two components is called. So four options are given which are shown on the screen. A, B, C and D. Please read all the options and remember the correct answer. The correct answer is homogeneous mixture of two or more than two components is called solution. Question number 2. Which of the following is an example of gaseous mixtures? You are given four options shown on the screen. Option A, camphor in nitrogen. B, solution of hydrogen in palladium. C, chloroform mixture with nitrogen gas. And option D is both A and C. Examples of gaseous solution. That is, camphor and nitrogen gas is a gaseous solution. Solution of hydrogen in palladium is not the correct answer. Chloroform mixed with nitrogen is also a gaseous solution. So choice A and B are gaseous solution. Please mark the correct answer. Option D. In amalgam of mercury with sodium, solvent is option A mercury, option B sodium, C is amalgam and D is none of these. We have to identify the solvent. Here amalgam of mercury with sodium is an example of solid solution in which mercury is liquid, is solute and sodium, that is solid, is a solvent. So answer is B. So B is the solvent, sodium is the solvent. Next question. What is the mass percentage of carbon tetrachloride in 22 grams of benzene is dissolved in 122 grams of carbon tetrachloride? I will read the sentence again. What is the mass percentage of carbon tetrachloride in 22 grams benzene dissolved in 122 grams of carbon tetrachloride? Four options are shown. So we have to analyze and mark the correct answer. So let us analyze. Mass of solution equals mass of C6H6 plus mass of CCl4. That is equal to, it is given 22 of benzene plus 122 of carbon tetrachloride. That what 22 plus 122 is equal to 144 grams. But mass of CCl4, therefore mass percentage of CCl4 is 122 divided by 144 into 100, that is 84.72%. This answer 84.72%. This answer appears as option A. Please mark it. Question number 5. What is the mole fraction of glucose in 10% W by W glucose solution? Four options are given. You have to analyze all of them using the calculation shown in the insert box. So number of moles of glucose is equal to 10 divided by 180. That is equal to 0.0555 mole. Number of moles of water is equal to 90 by 18 because 100 minus 10 is 90. This is the moles of water divided by the molecular weight of water 18. That's equal to 5 mole. Therefore, the number of moles of solution will be equal to 5.0555. That is this plus this, equation 1 plus second equation. So therefore, mole fraction of glucose will be equal to number of moles of glucose that divided by number of moles of solution. Therefore, that is 0.0555 divided by 5.0555. That is equal to 0.01. So let us mark it. Next question. When 1.04 grams of BaCl2 is present in 10 to the power of 5 grams of solution, the concentration of solution is. Four options are available on your screen in parts per million. So let us analyze and mark the correct answer. Therefore, concentration of solution is 1.04 divided by 10 to the power of 5 grams into 10 to the power of 6. This 10 to the power of 6 is for calculating parts per million. That this comes to 10.4 parts per million. So option B is the correct choice. Question number 7. What will be the mole fraction of ethanol in a sample of spirit containing 85% ethanol by mass? Four options are given which are appearing on your screen. Let us analyze it. Therefore, percentage X, that is mole fraction X of C2H5OH is equal to N of C2H5OH divided by N of C2H5OH plus N of H2O. So therefore mass of C2H5OH is 85 grams. It is given 85. So therefore molar mass of C2H5OH is equals 46 grams. Therefore mole fraction N of C2H5OH is 85 divided by 46, that is equal to 1.85 mole. Mass of water is 100 minus 85 because it is a 85 ethanol by mass. Therefore 115 grams. Mass of water is 15 grams. Therefore N mole fraction of H2O is 15 by 18, that is equal to 0.833. So therefore molar fraction is XC2H5OH equals 1.85 divided by 1.85 plus 0.833, that is equal to 0.69. This option is given in A. Please mark it. Next question. What is the molarity of solution containing 10 grams of NaOH in 50 ml of the solution? Four options are given. You have to analyze and mark the correct answer. So calculations are required. Number of moles of NaOH is equal to 10 by 40. That is given 10 grams in total solution is 500 ml. So it is 10, the number of moles will be 10 divided by 40. That is equal to molarity M, capital M will be equal to 0.25 divided by 500 into 1000. That is equal to 0.5 mole per liter. This answer is available as option C. Next question. Next question. How many Na plus ions are present in 100 ml of 0.25 m of NaCl solution? Four options are given. Option A, B, C and D. You have to analyze and mark the correct answer. So let us analyze. Number of moles of NaCl is equal to M into V. That is capital M is molarity into V divided by 1000. So molarity is 0.25 m into 100 divided by 1000, that is equal to 0.025. Further, NaCl gives his breakup is Na plus and Cl minus, positive ion of Na and negative ion of Cl. Therefore, number of moles of Na plus ions will be is 0.025. We have calculated previously. Therefore, number of Na plus ions will be equal to 0.025 into 6.023 into 10 to the power of 3. that is equal to 1.505 into 10 to the power of 22. So this option is available in option B. Next, how many grams of NaOH are present in 100 ml of 0.5 m solution? So four options are given. You have to analyze, calculate and give the correct answer. So number of moles of NaOH is equal to m into V divided by 1000. So capital M is 0.5, that is molarity, into 250 ml of the solution divided by 1000, that is equal to 0.125. That is equal to mass of NaOH is equal to 40 into 0.125, that is equal to 5 grams. So this answer is available as option C. Next question. Molarity is a function of temperature because, so we have to give reasons. Four options are given. So you have to read it. Please read it. Volume depends on temperature and molarity involves volume. Molarity involves non-volatile. This is wrong. Number of moles of solute change with change of temperature. That is also wrong. Molarity is used for polar solvents. This is also wrong. So the correct answer is A. You remember and mark it. Next question is express the terms representing the formulae. Following formulae. So different formulas are given. Number of moles by solute, volume of solution in liters. That is, let it be W. It is given as W. And number of moles of solute divided by mass of solvent in kg is X. Number of moles of component divided by moles of fraction is given as the symbol Y. And fourth one is mass of component divided by mass of solution Z. So four formulae have been given. Now you have to see what is the question. This is the given statement and you have to see the question. So molality. Molality, what is the definition? Molality is, so we have to identify whether W is a molality or X is molality or Z is molality. This you have to examine and mark the correct answer. The correct answer is C because molarity, number of moles by volume is molarity and number of moles of solute by mass of solvent is molality and number of moles of component divided by number of moles of solution is a fraction, mole fraction, because numerator denominator is moles. And the fourth one is mass to mass. So it is a mass fraction. So W should be molarity and X should be molality and Y should be mole fraction and Z should be mass fraction. So therefore answer C is the correct answer. You please mark it. Answer C is the correct answer. With this we come to the conclusion of section 1.2, that is expressing the concentration. In the next chapter, next session, we'll continue with discussions on solutions given in class 12 chemistry. Till then, goodbye.